we start, so mostly today is going to be practicing. You guys are going to be working in your groups, practicing taking derivatives of complex functions. How many of the derivative formulas can you remember? All right, we're going to fill in this little table here. Just take a couple seconds and fill in all the formulas you can remember. All right, so let's fill some of these in. The derivative of x to the n, we would apply the power rule, and what do you get when you take the derivative? Yeah, nx to the n minus 1. And I gotta turn my smartboard on. Come on. It's not on. Is nx to the n minus 1. Derivative of e to the x? E to the x. Derivative of a to the x? Yes, a to the x times the ln of a. Derivative of sine x? Derivative of cosine x? Negative sine. Derivative of tangent? Yep. Derivative of ln x? 1 over x, that was from last class. Derivative of arctan x? Close. 1 over 1 plus x squared. And the derivative of arcsine? Yep, that's it. So there's our major derivative formulas that we know so far. If a function doesn't look exactly like one of these formulas, though, like exactly, you can't use those formulas. Okay? Instead, you need to use one or more of the following 5 rules to break the function down until it looks like exactly one of these formulas. So here's what to look for. First, sum and differences, right? If you have the sum or difference of 2 functions, you want to take the derivative, you can just take each one separately. Okay, so does the function consist of multiple terms separated by plus or minus? If yes, then treat each term as its own derivative problem and then just add or subtract the derivatives. All right, then look for constant multiples. If the function, what to look for, is there a constant which the rest of the function is multiplied by? In that case, find the derivative of the rest of the function and then just multiply by the constant. That's when I say, like, this one just comes along for the ride. That's the coefficient will just come along. Then, so those are the simplest 2 things that you could have. And then we move on to things like the product rule. Okay? If the function consists of 2 functions that are multiplied together, use the rule to find the derivative of the product. Okay, but first, remember that the derivative of f times g is not f prime times g prime. Okay, you have to do f times g prime plus g times f prime. And another caution, remember that an expression like cosine of 3x, that's a composition, not multiplication. People will often try to use the product rule there, treating cosine as the first function as 3x as the second function. But that's not multiplication. That is 3x being plugged into the cosine function. So that's a composition. And then caution number 3, if there's a product inside part of the function, you have to use a different rule before getting to the product rule. So we'll have some examples like that. And then we have the quotient rule. If the function has consists of 2 functions, one divided by the other, use this rule to find the derivative of the quotient. Okay. Always remember that the derivative of f over g is not f prime over g prime. It's the more complicated looking derivative rule. And if there's a quotient on the inside, you have to use a different function before using the quotient rule. And the quotient rule comes when you do the then multiply by the inside function part of the chain rule. And then finally, we have the chain rule, right? If I want to find the derivative of a composition f of g of x, it's f prime of g of x times g prime of x. Or you can express it in Leibniz notation, dy dx is equal to dy dz times dz dx. All right, what to look for. If none of the other above rules helped, or the function contains a simpler function within it, you can either identify the embedded and overriding functions, that is the inside and the outside function, or introduce a new variable z and set it equal to the simpler function and use the Leibniz notation. And if there's a composition inside a product or quotient, use the product or quotient rule first. All right, so here's some examples for a little strategy guide. So these are things to notice. So things you want to take the derivative of. In this first example, I would notice, oh, that's two things I know how to take the derivative of added together. So I can just take the derivative of each one separately. 3x to the fifth, this is a constant multiple rule, right? So I can just ignore the 3, take the derivative of x to the fifth, and then multiply by the 3 after, right? And so I would get 15x to the fourth. X to the fifth sine x, that is a product of two functions I know how to take the derivative of that look exactly like the functions from the little chart we filled out. So I use the product rule. Here, x to the fifth over sine x, it's a quotient of two functions I know exactly the derivatives of, right? X to the fifth and sine x look exactly like functions that I have formulas for. So I use the quotient rule. Sine of x to the fifth is a composition, right? So you want to identify the inside and the outside function, take the derivative of the outside function, then multiply by the derivative of the inside function, right? So for sine x to the fifth, the derivative of sine of some stuff is cosine of that stuff, but then times the derivative of the stuff, 5x to the fourth. And sine of x to the fifth looks almost the same, except that we've switched which function is inside and which function is outside. So in this one, you would apply the power rule first, because that's the outside function. So apply the power rule to the stuff of sine x, and multiply by the derivative of the stuff, cosine x. And then we start getting more complicated, right? We can really complicate things by having a quotient with a product inside of it, right? I have a quotient and a product in a denominator. So I have to apply the product rule within the quotient rule. And then I have a product rule with a composition and a composition with a product on the inside. So let's go through a few of these tougher differentiation problems together. And then I will leave you to do some work on your own. Okay, so I have the square root of 2 all raised to the x times the ln of x. So that looks to me, the first thing I see is that is the square root of 2 raised to some stuff, right? What is, so let's just put a little box here and pretend that that was just a plain old x, right? What's the derivative of square root of 2 to the x? Yep. That's it. Right? Because all I asked for was what is the derivative of the square root of 2 to the x. If that was just a plain old x, that would be the derivative, right? But it's not just a plain old x, right? It's some stuff. So I have to put the stuff in that box, x ln x. And then I have to multiply by, so I've applied the outermost derivative rule. I had square root 2 to some stuff. The derivative would be square root 2 to that stuff times the ln of square root 2. But then you have to multiply by the derivative of the stuff. So now I have to multiply by the derivative of x times ln x. How am I going to go about that? Yeah, it's a product. And in fact, maybe I'm just going to write down times d dx of x ln x. Right, just so that I keep track of what I'm doing. So this was a chain rule problem, square root 2 to some stuff. So the derivative is square root 2 to that stuff times the ln of square root 2 times the derivative of the stuff x ln x. All right, so then in my next step, I still have the part of the derivative I already did. And then I have to multiply by the derivative of x ln x. So now this is a new derivative problem. I should start fresh here and think about how I would take the derivative of x ln x. It's a product of two functions that I know how to take the derivatives of. So it's going to be x first times the derivative of the second, and the derivative of ln x is 1 over x. First times the derivative of the second plus the second times the derivative of the first, which is 1. And then x times 1 over x is 1. Ln x times 1 is ln x, so I can simplify this to that. Questions on any of the steps here? No? All right, should we do another one? All right, let's look at e to the cosine of the ln of x squared plus 1. Okay, what's my outermost function? E to the x. Okay, so that's what I start with taking the derivative. That is e to just a whole bunch of garbage, right? Think of that as e to just a bunch of stuff. The derivative of e to some stuff is e to the stuff times the derivative of the stuff. Okay, so y prime is going to be e to all this stuff, the cosine of the ln of x squared plus 1, times the derivative of all that stuff, the cosine of the ln of x squared plus 1. Good so far? So the derivative of e to some stuff is just e to that same stuff times the derivative of the stuff. Okay, so now I have to work on the derivative of the stuff part. So this is e to the cosine of the ln of x squared plus 1 times the derivative of the cosine of the ln of x squared plus 1. What's the outermost function? Cosine. What's the derivative of the cosine of some stuff? Yep, negative sine of the stuff times the derivative of the stuff. So all this stuff, the ln of x squared plus 1, that's just some stuff. It's the cosine of some junk, right? So the derivative of cosine is negative sine of this junk here, ln of x squared plus 1. So the derivative of cosine is negative sine. Stuff inside stays the same. Then I have to multiply by the derivative of the stuff. The derivative of the ln of x squared plus 1. All right, so I'm just going to copy down what I already have here. E to the cosine of the ln And that's times the negative sign of the ln of x squared plus 1 times, okay. Now I'm going to work on the derivative of the ln of x squared plus 1. What is the outermost function there? Ln. That's the ln of some stuff. Okay, so what is the derivative of the ln of some stuff? 1 over that stuff times the derivative of the stuff. So it's going to be 1 over the stuff, which is x squared plus 1, times the derivative of the stuff, which is x squared plus 1. And what's the derivative of x squared plus 1? 2x. So here's my last line here. Y prime is going to be e to the cosine of the ln of x squared plus 1 times the negative sign of the ln of x squared plus 1 times 1 over x squared plus 1 times 2x. That's all multiplication. So it was a composition of 4 functions, so we had to use the chain rule 3 times. All right, when you look at C, what's the first thing that you see? What jumps out at you? Quotient. Okay, good. So yeah, let's start with the quotient rule. So Z prime is going to be the denominator, W, arc sine W, times the derivative of the numerator, which is what? Yeah. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Ooh, how am I going to take the derivative of that denominator? Product rule. That's W times arc sine W. So that's going to be a product rule, which means that this derivative is going to be an involved problem all on its own. So here I might just write d dw of W arc sine W and come back to it. All divided by the denominator squared, W arc sine W squared. Okay, so I'm almost done. I just have that derivative of the denominator to do. And I decided to save it so that I wouldn't get lost in which derivative I was taking. All right, so Z prime is W arc sine W, that's my denominator, times the derivative of the numerator, 2W, minus the numerator times the derivative of the denominator. So I need the derivative of W arc sine W. So this is a product, right? W times the arc sine of W. So I use the product rule to get this. I'm going to put a big square bracket here. So the product rule is first times the derivative of the second. And the derivative of arc sine W is 1 over the square root of 1 minus W squared. I think it's minus. First times the derivative of the second plus the second, which is arc sine W, times the derivative of the first, 1. I could simplify a little bit, right? I could, in this product rule, I could put this W on top of the fraction. And I didn't have to write this 1 down because times 1 doesn't mean anything, or gives you the same thing. So I could simplify a little bit, but it's not going to make that much of a difference, so I'm just going to leave it. And I used up all my room, so I got to move D to another page here. Good enough. All right, I have 200 e to the negative 0.1 t plus 100 e to the negative 0.1 sine of pi t times t. All right, so what's the first thing that jumps out at you? It's a sum, which means I can do these two derivatives separately. So I've got two derivative problems to work on here. I'm going to take the derivative of each term. So f prime of t is going to be the derivative of the first term plus the derivative of the second term. What's the derivative of this first term? Constant multiple. Yep, constant multiple. So I can just write the 200 down, right? And then I can just take the derivative of e to the negative 0.1 t. And I'll multiply that times my 200. So e to the negative 0.1 t. How am I going to take the derivative of that? Yep. That's e to some stuff, right? So the derivative of e to some stuff is just e to that stuff times the derivative of the stuff. And the derivative of negative 0.1 t is negative 0.1. So that can be simplified quite a bit, but I'm going to just leave it for now. And I'll simplify it in the next line. For now, I'm going to move on to the next derivative, the derivative of the next term. So again, I have a constant multiple, so I can just write that 100 down and multiply it by whatever I get when I take the derivative inside. Oh, that's next to it. All right, so what comes after the 100 is e to a bunch of stuff, right? What's the derivative of e to some stuff? Well, I know you guys know. E to the stuff times the derivative of the stuff. So I have 100 times e to this, all this stuff, negative 0.1. I'm going to move the t to the front because it just looks more normal to me, times the sine of pi t. Okay, so that is e to the stuff. Then I have to multiply by the derivative of that stuff. d dt of negative 0.1 t times the sine of pi t. Okay, so I didn't try to even take that derivative of the inside stuff because it's a complicated problem in and of itself. So I decided, okay, I'm just going to write down the derivative of this stuff, and I will take that derivative in the next line so that I don't get lost in what I'm doing. So this first term I can simplify by multiplying the 200 times the negative 0.1. So I get negative 20 e to the negative 0.1 t. And then over here, I have 100 e to the negative 0.1 t sine pi t. And then I have to multiply by the derivative of negative 0.1t times the sine of pi t. What rule is going to be the first rule I have to apply here to take this derivative? The product rule. This is the product of two functions, negative 0.1t times the sine of pi t. Product rule. So I'm going to have first negative 0.1t times the derivative of the second. What is the derivative of the sine of some stuff? Cosine of that stuff times the derivative of the stuff. So sine of pi t, its derivative will be the cosine of pi t times what? Pi. Good. The derivative of pi t is pi. So this is first times the derivative of the second plus the second, which would be the sine of pi t, times the derivative of the first. What is the derivative of negative 0.1t? Negative 0.1. All right, let's see. Can I simplify this? I think so. So this term is as simple as it's going to get. I have a factor of negative 0.1 in both of my terms here that I have with the product rule. So if I were to factor that negative 0.1 out from both of those terms, then I could multiply it by the 100 and get a negative 10. Okay, so I factored out the negative 0.1. So all I'm left with here is pi t cosine pi t. Pi t times the cosine of pi t. And in the next term, I factored out the negative 0.1, so I'm just left with a sine of pi t. So the trick is just do one thing at a time, right? Apply one rule at a time. Don't try to take the whole derivative in one step. When you come upon, taking the derivative of the inside, or if you're doing a product rule within a quotient rule, when you're doing a rule within a rule, it really helps to keep your work organized. If you come across something that's going to be difficult derivative on its own, just write the derivative of it, ddt of this thing, and come back to it, so that you can keep, you can kind of keep the big picture of the problem, what you're focused on, and then go back and do the derivatives within the derivatives. Okay, so your homework tonight is 1 through 73 odd, from pages 168 to 169 of your book. It may take you several days to get through this assignment. Check your answers with the answer key in the Math Studio or the library. As you work through the exercises, recognize that you might have the right answer, even though it doesn't match perfectly with the answer in the answer key. It all has to do with simplifying, right? You can find solutions, not just the answers, to all of the problems in the binder in the Math Studio or the library. And the problems that that you're going to be working through here are similar to the problems in the next project. So you are going to have the rest of class get started on this ginormous homework assignment. If you don't have your book, you could start on the project, right? Because that is also some good derivative practice.